Okay. So good morning or good afternoon, everyone, and thank you for being there. So today we have the pleasure to welcome Professor Shijie Zhong from the University of Colorado, and he's going to talk to us about the structure and dynamics of terrestrial planets, which is a topic we haven't had many webinars on. So very happy to have you, Shijie, and the floor is yours.
Okay. Well, thank you, Catherine. Yeah, it's my pleasure to give this talk. I guess today what I like to do is to really show how mantle dynamics can explain some of the most fundamental features that we see, I guess, on some of our terrestrial planets. So this actually would include uh, the Mare basalts on the moon, sources rise on Mars, and also supercontinental cycles on Earth. So, of course, before I start, I like to really acknowledge the contributions over the years from my former students, postdocs, who are actually listed here at the bottom of these slides. Okay. Um, so let's see. Um, yeah, and so here is an outline of my talk. And so at the beginning, I like to, basically present you some of the important observations of the larger scale, or we call it long wavelength structure of, the Earth, the Moon, and the Mars. Then after that, and I will discuss the dynamic mechanisms or the dynamic formation of large-scale structure from mantle convection or mantle dynamics. By large scale, I mean really the longest wavelength features that we see for these planets. Okay, and in particular here, basically there are four topics that I like to discuss here. Okay, and they're all related to the mantle dynamics as we will get there. Okay, then of course at the end there will be a conclusion. Okay, so now let's look at the Earth, okay? Right, first we look at the Earth, we call the Earth's mantle structure as seen from seismic tomography, right? This is really just how the seismology being applied to image the Earth's interior. For this particular slice, what we see here is a seismic shear wave anomaly in the lower mantle at about 2,300 kilometer depths. What you, of course, see here is what we often call the degree 2 structure. That is, you have two, we call it super plumes. One is the African super plume, and then the other is a Pacific super plume. Okay, and then this really represents about this yellow color or red color regions, and they're seismically slow anomalies. Often they represent relatively hot, warm structures, and then of course in between is what we call the circum-Pacific subduction. In this here is kind of blue greenish color. So they often represent relatively cold anomalies. Okay, right? Um, so before I start talking about sort of various spherical harmonic degrees, I just want to remind you when we say degree 1, degree 2, those are really in terms of spherical harmonics. So of course, on a spherical surface and spherical harmonic functions, they kind of tell us really about the wavelengths, right? So often the degree 1, like what we have here, the degree 10 or 11, and they're really just the hemispherical structures. So the 10, for example, represent the northern hemisphere, southern hemisphere differences. 11 means really the east-western hemispherical differences. This is like the longest wavelength, the largest scale features that we can see, for a planet. Okay, right. Then we go to degree 2, and the shorter wavelengths. And so this, for example, 20 represent the difference between equator and the two poles, right? So etc. So degree 3 and etc. There are even shorter wavelength features. Okay. But today in my talk here, mostly I'll deal with degree 1 and degree 2 structures. Those are the largest scale features we see for various planets, okay, right? Now, if we take the seismic tomography, if we actually kind of do like a spectrum analysis, so what you see here is a depth versus spherical harmonic degree. So the color shows how important the structure is. So what you actually see is throughout the Earth's mantle for present-day Earth, that is the degree 2 is the strongest structure, that is the red all the way, right? Except near the very surface, then you see some of the degree 1 features, okay? So basically we're sort of saying the seismic tomography suggests that degree 2 is the most important structure for the Earth today, okay, right? Now, let's just talk very quickly about degree 2, the significance of degree 2 structure. For example, degree 2 seismic structure, we know that it actually really correlated very well with the long wavelength geode. And this is gravity anomalies, right? So what you see here, this is degree 2 and degree 3 geode anomalies. And you can sort of see and this green or the yellow colors really correlate very well with the seismic anomalies, right? And so which suggests that what we see, the gravity anomalies, long wavelength gravity anomalies, is really controlled by the seismic structure, long wavelength degree 2 seismic structure in the mantle, okay? Now, the one question we can actually ask, can we even have even longer wavelengths than degree 2? Well, the only wavelength that is longer than degree 2 would be degree 1, right? So there are actually hints, not for present day, but for the past, for the Earth's past, that is the supercontinent period. So we know there's a supercontinent Pangaea exists. That's like between 330 and 180 million years ago, right? So that's when all the continental blocks are together, okay, right? This form this so-called supercontinent Pangaea. Then even before that, there's another period, between 900 and 750 million years ago. This is a supercontinent called Rodinia, okay, right? And then of course, when all the continents are in one hemisphere, and that's actually degree 1 structure at the surface, and also possibly degree 1 structure in the mantle. Then of course, what we're talking about is not for present day, it's really for the past, for the Earth. Okay, right. So the supercontinent events, they're really important in terms of the tectonics and the magnetism for the Earth. And so, for example, we know all the major mountain belts were actually created during the supercontinent events when continent collide, right, to form supercontinent. That's when that's when the major mountain belts got formed, right? And also, if we look at the history of the sort of magnetism. What you see here, the vertical axis is the time. Present day is 0 here. That's present day, right? And so this is then the horizontal axis here is really the frequency of the magnetism, okay, averaged, right? So this is per 100 million years for 100 million years. Then what you see here is the magnetism is the strongest during the supercontinent breakup, like a Pangaea breakup. You see this peak in volcanism or magnetism, right? And you see the minimum in magnetism when the continent come together, like a Gondwana land, sort of formation, and then also same with Rodinia, okay, right? And so as you can see, right, really the supercontinent events are very important. Okay, right. So yeah. Now let's actually move on to the moon. Okay. So this is a picture. Basically the near side of the moon, and this is the side that we often see, right, when on the Earth. Then this is the far side of the moon that actually we cannot see on the Earth unless you fly spacecraft, right, and fly back to the on the back side of the moon, right? And the color here really, this is like basically the kind of color that we often, we would see from the Earth. This dark color really is what we call the marble salts, right? And so the marble salts turns out that actually it kind of formed a long, long time ago, about 4 billion years ago, right? Really, and you can only find this dark stuff on the near side, okay? And this is what we call the degree one structure, right? One hemisphere that is different from the other hemisphere, right? And it turns out that the marble salts actually that is and they show some distinct chemistry. That is, what you see here is a remote sensing, results for this is really showing the very high concentration of FeO, right? And this is iron, right, oxide. And so as you can see, where you have marble salt, if you remember that picture I showed you earlier, right, that dark stuff, and then you actually see this high concentration of FeO, okay, right? But where you actually, for the far side, you don't really see much, okay, right? It turns out that the marble also actually really accounts for about 30% of the surface of the near side of the moon, okay, right? Now, if we look at another sort of degree one structure or the global asymmetry, that is the crust thickness, it turns out that, on the near side, and the crust tends to be thinner than the far side. Okay, right. Um, then there's another global asymmetry. I put a question mark here that is actually related to the deep moonquakes. Just like Earth, the moon actually also has a lot of moonquakes. Okay, and those deep moonquakes occurred at about 1,000 kilometer depths, and they're driven by the tides. Okay, so what you actually see here on the near side, where you have a lot of marble salts, that's also where you have, this is detect through the Apollo mission, right? And then you also you see a lot of deep moonquakes. They're represented by the triangles here. And by the way, the squares you see here, those are actually this is the seismometers sent by the Apollo, sort of astronauts. Okay, right. So I put a question mark here. That is because it is possible that the far side may also have a lot of moonquakes, but because the seismometers were placed on the near side, maybe would not be able to detect the events or the moonquakes on the far side. So, but it is still the question to be resolved because, humans, we haven't not yet put any seismometers on the far side yet, but it's going to be happen. It's going to actually happen in the next maybe, few years. Okay, right. So anyway, now let's go to Mars. Okay. Mars, actually, there is two very important sort of global asymmetry that you see from the surface. And the first one is called Sars's rise. That's actually the region that I circled here. And so the second one is called, what we call the cross dichotomy. Okay. So now I'm actually going to explain in more details about these two degree one structure or global asymmetry for Mars. Okay, right? And first, let's look at the global assembly. This is cross dichotomy. Okay, right. Um, so the cross dichotomy is really the hemispherical asymmetry or the degree one structure in elevation. So we know the southern hemisphere, the red color, they're about 5 kilometers higher than the blue region, the northern hemisphere. Okay, right. And also, this asymmetry, the global asymmetry also really can be seen from the cross thickness between the northern and the southern hemispheres. So the cross dichotomy is really the sort of asymmetry between northern and southern hemispheres. Okay. Um, and we also know the crust dichotomy is really the oldest feature on Mars. They may actually be formed, in so-called pre-Noachian, and that's really older than 4.1 gig years. Okay, as various, evidence suggest. And so then the second thing is that this is Sars's rise that I kind of highlighted here in red circle, right? And this is actually another sort of global asymmetry degree 1 structure with a topography high of several kilometers, but this actually is really in equatorial region, right at the cross-dichotomy boundary, and it really occupies about a quarter of Martian surface. Okay, right. Then this, so there are a lot of volcanism happening in this region. In fact, in the last 4 billion years, really, this is like 90% of the volcanism and tectonics actually occurred in this region. But it actually appears that is the volcanism start about 4 billion years ago in this region called some Asia. That's this A. Then there's a subsequent migration of central volcanisms towards the dichotomy boundary. Okay, but largely, by 3.8 billion years ago, and the SARS is largely formed. Okay, so the formation time is relatively rapid. For about 200 million years, from 4.0 billion years to 3.8 gig years ago, and that actually the SARS is kind of largely formed. Okay, right. So if we kind of sum up very quickly about the Mars, so there's a cross dichotomy, which is the oldest feature, right? The SARS rise is younger, but not by much, and formed relatively quickly. So the cross dichotomy is a degree 1 structure with a thickened crust centered, near the South Pole, right? But largely is a dichotomy between North and South, right, hemispheres. Now, SARS is also degree 1 structure, but centered at the dichotomy boundary, largely West hemisphere versus East hemisphere differences. And then there's a volcanic center migration, right, for SARS from the highlands to the dichotomy boundary. Okay, so I guess what so by now I kind of finished the introduction section. That is, I kind of highlight all this globally, very, very long wavelengths, large scale structures that we see for the Earth, the Moon, and Mars. Okay, so what I actually want to do next is really to show, to demonstrate, to you that mantle dynamics, that is the mantle convection, we know is a fundamental process, right, that controls evolution of the planets. I want to really show you that mantle dynamics may provide, explanation on how, this non-wavelength structure can actually occur for, this sort of those planets. Okay, so now let's first move on to and talk about in general how mantle convection can actually form structures. Okay, so in early days, when we could only do convection simulations with constant viscosity. That is, it's really assuming the planet like as a homogeneous body, and then back then, at a relatively small Rayleigh number. Rayleigh number is really a measure of vigor of convection. Um, so what people showed, basically, you could only get a really, like a cubic kind of or tetrahedron kind of structure, which is certainly not like nothing like a degree 1 or degree 2 structures, right? So then subsequently, people can do more sophisticated simulations using temperature-dependent viscosity, maybe higher Rayleigh number, like what I actually showed here in one of my study. Then what you see is, you would go get even shorter wavelengths. All the blue and the yellow, features. They're basically convective down warnings. The blue up warnings in yellow. So the up warnings, they're hot, they're boiling, so they're up warnings, right? And blue, they're cold, and they're down warnings. Okay, right. So, it's actually it's been kind of challenge as to how to produce really long wavelength structures from convection, right? Given that most of convection studies is really show you that, relatively short wavelengths, right? So it's really a question here is how to generate long wavelength structure, okay, in terrestrial planet mantle. So Now, one thing we can, sort of speculate or we can think about that is possibly the viscosity stratification. That is, we know if you look at how temperature varies with depths, in the Earth, in the Earth's mantle. So we know that, of course, as we increase depths, then the temperature will increase. And so there's actually the red line is the solidus, that's a melting curve. And then the black, sort of curve here is really is what we call the geotherm, right? And so you can sort of say this is like the mantle eddy bed, okay, right? So as you can see, when you get to the shallower depths in the upper mantle, those two curves they actually approach to each other, which means that the Earth's mantle actually approach to solid disks, approach to the melting point, right? So when the material reach to the melting point, the viscosity tends to be, tends to decrease. Okay, so indeed, that from various studies from physics and post-glacial rebound and the gravity observations, that all the studies that suggest indeed the up mantle tends to be much weaker than the lower mantle, right? This is viscosity in horizontal axis versus the depths, okay, in y, in vertical axis, okay. So then it turns out that this is this viscosity increase with depths. They tend to help increase the convective wavelengths, as previous studies suggest. But it has been a challenge to really get convective wavelengths, say, longer than degree 6, okay? And so this has actually been kind of demonstrated in the past. Now, let's actually look at the, do a quick, we call it radiatorial instability analysis, and really to show how the viscosity layering may help to produce long wavelengths, okay? And so in this kind of analysis, of course, we have a metonic core here, right? Then we kind of divide the Earth's mantle into two layers with different viscosity. The viscosity eta U is the upper layer viscosity, then eta L, that's lower layer, lower mantle viscosity. We actually have two different densities for these two layers, such that the upper layer is heavier, and then the bottom layer. In such a way that this configuration is unstable intrinsically, right? And so it's gravitationally unstable. Then what we actually want to do here is to kind of analyze when this instability happens, what would be the growth rate of instability, and how that actually the growth rate would actually vary with the wavelengths and also with the viscosity variations. So what we actually showing here is that suppose this is this red circle that is actually the density interface. It's at somewhere middle of the mantle, okay, right? And then this is actually case where the viscosity of the two layers, up and bottom, the ratio is 1, so they're equal viscosities. So in this case, what you see is the normalized growth rate of the instability in y-axis, and the horizontal axis is spherical harmonics, or degree, 1 to degree 100 is different wavelengths. So what you see here is that the most unstable, wavelengths, that is the wavelengths for which the instability will grow the fastest. Sorry? Oh, there was a question?
No, I think someone was not
Oh.
muted, so
Oh, okay, sure, yeah,
sorry.
that's all right. Yeah, feel free to ask questions if you want, okay, right? So basically what you see here is the most unstable wavelengths, it actually occurred around degree 7, 6, okay, in this case when the viscosity is constant, right? So what we actually want to achieve is really, it's like long wavelengths, like degree 1, degree 2, that's somewhere in this region. Clearly, those are not, those wavelengths actually in this case actually quite stable. But what if we start to vary the ratio of viscosity? So if we net ratio decrease from 1 to 0.1 to 0.01. That is actually in the case of 0.01, that's actually the upper layer viscosity is only, 100 times smaller than the lower layer, right? So in that case, we actually can see the growth rate of instability is the largest at degree 1, okay? So this actually suggests that the viscosity layering will actually really help to promote long wavelength convection. Okay, right. Now let's actually see how the amount of convection simulation would actually reproduce this kind of results, right? Or conform this, right? So I guess also I would say a smaller core, the metonic core, if the core smaller, then that would also promote long wavelength degree 1 stability, okay? Right. So now this is one calculation. This is actually the sort of two-dimensional axis symmetry calculation. So what we see here, there's a symmetry along this vertical axis here. So you can think there's like a rotational symmetry, okay? But what we see here is just one slice of the planetary mantle, right? So we have an upper layer, we have a lower layer. In this case, we actually also have the so-called stagnant convection. So we actually, and the surface is, essentially is a high viscosity, is not moving at all. So what you see here, in this case, the ratio of viscosity is 1, meaning that, the mantle is really got a constant viscosity except the high viscosity lithosphere, okay, right? So now the color really means the temperature. So the red is hot, the yellow and green, they're cold, and the arrows here, the velocity vectors, okay? So what you actually see again, in this case, the constant viscosity, you have a lot of down warnings, right? Down warnings. And you also have up warnings, many of them. So this is nothing like long wavelength convection, right? So this is kind of like what the Rayleigh-Taylor instability I showed you, right? For constant viscosity, the most unstable wavelengths or the preferred wavelengths actually occurred around a degree 6. That's essentially what we see here, okay, right? You can count like a 6 downwards, more or less, in this case. Now, if we reduce this ratio to one kind of 500s, right? And then all of a sudden, the convection would happen in such a way that you only produce one up warning in this hemisphere, right? And then the velocity vectors also kind of point to this is the up warning, right? So this is showing that at least in 2D convection simulations, the viscosity layering or to have a weak upper layer would really help promote degree 1 convection. Then we can also do this simulation in sort of three-dimensional geometry. So this is 3D spherical convection simulation, essentially showing that you don't really actually need such viscosity layering. In this case, a factor of 25 or 30, it's sufficient to produce this we call one plume convection. Is only one upwarding plume, right? And so we think such degree 1 convection or this one plume of hot welding may actually help to explain this hemispherical structures like marble salts, Martian cross dichotomies, or even sources. The reason, of course, if you this is one plume that's hot, right? And if that one plume, you only have one plume, then the one plume, if that occur for the moon on the near side, then that's how you actually produce all the marble salt volcanism, right? Not in the other hemisphere. And same with Mars, if you have one plume like this, then you could actually produce extra melting that give you the extra crustal material, so you can have crustal dichotomy or surface rise for that matter, right? So we think this is actually quite important for at least for this so-called this stacking the convection, okay, right? Which is essentially almost all the terrestrial planets we know. There are what we call a stacking the convection, except Earth. Earth got a plate tectonics, right? So the stacking the convection is really happening everywhere for other terrestrial planets, okay, right? So now let's actually ask a question, can we actually possibly do, really explain, the cross dichotomy and Martian cross-dichotomy and the tharsis in a what we call the unified model. Well, we already kind of talked about cross-dichotomy, right? It's the kind of oldest feature on Mars is a degree 1 structure, but it's north versus south. And SARS is a degree 1 structure, but is younger, but not by much, right? And it's also sort of cross-dichotomy, it's the west hemisphere versus east hemisphere, okay, right? And there are also significant volcanic center migrations, right? So the question here is we kind of ask, there might be some genetic connection between the cross-dichotomy and the tharsis, right? So the question is really, can the same one plume structure be responsible for producing both cross-dichotomy and tharsis in a unified model? Okay, so what I actually want to present here is a hypothesis that is and yeah, this model, this unified model, is possible through what we call the differential relative rotation between the plume and the lithosphere. Okay, and so here is a sort of the idea. Let's actually first talk a little bit about the differential rotation of lithosphere. Okay, relative to the mantle. So this is what we actually often call a toroidal plane motion. Okay, right. So the toroidal plane motion, what is the toroidal plane motion? Well, if we know the Earth got plate tectonics, right? So what you're seeing here is a present day, sort of plane motion for the Earth, right? So the vectors, of course, showing the plane motion. Now we know for a long time, if you actually, there are two kind of component in this plane motion. One is what we call the poloidal plane motion, which is really related to the seafloor spreading, subduction, right, and anything related to going related to the material going up and down. Okay, right, and that's what we call the poloidal plane motion. Toroidal plane motion, on the other hand, is associated with the plane spinning and also the transform fault, like a St. Andreas transform fault, right? And so those are actually the motion, what we call the toroidal motion. It turns out that the degree 1 toroidal motion is like the entire lithosphere and rotate relative to the mantle altogether. It's called differential rotation of the entire lithosphere. And for the Earth, such rotation is quite significant. With the rotation pole centered at the Indian Ocean. Okay, so and we also know the way to produce, the toroidal motion is to have horizontal variation or lateral variation in viscosities. Okay, so for example, if you have cratons, right, cratonic material, uh, so the cratonic material can actually have this sort of keel, right? Cratonic keels, and they can help to generate toroidal motion. Okay, there's the keels that tends to have high viscosity because the continental keels, when they're formed, and they basically kind of develop there's this is a dewatering effect. Okay, the water being removed from the cratonic keel, so viscosity tends to be high there, okay? And so I would argue that for one planet, that is a stagnant convection, such as Mars, and the differential rotation of this spherical shell is really the only possible um, plane motion, okay, relative to the mantle. So the question here is if how this actually can happen, right? Whether this is sort of the idea, right, and or the hypothesis. And so let's see how we actually can show this, this actually could happen. So now, so the idea behind this is that, okay, suppose you have this one plume scenario, right? So you have one plume that produces sort of upholding the volcanism, right? So that volcanism will actually lead to thickening the crust. Then for Mars, that could be, could actually produce the crust dichotomy, right? And then as a result, this is, melting, then there's this melt residue material, right? So this is showing here as a blue, this is, lighter blue, and melt residue, as I mentioned earlier, the melt residue viscosity actually tends to be higher because the water being removed, or you have this devolatilization process. Okay, so that's how you actually produce this high viscosity for the melt residue immediately below the lithosphere. Okay, right. Then we think, together with the melt residue or the thickened lithosphere above the plume, then this actually may induce the degree 1 toroidal field, or the differential rotation between the lithosphere and the mantle. And then this could possibly provide a unified model to explain both crust dichotomy and the tharsis. So I'll actually show you how we actually can, how this can happen in mantle convection. So in this case, this is time A at the beginning, right? And we have up warnings. Actually, in this case, you actually have 2 up warnings. And now this, this light blue cap is really what we call the melt residue layer. Okay, so you suppose we have this melt residue high viscosity, with high viscosity melt residue, right? That actually kind of happened in this one hemisphere, right? And then what actually happened subsequently would be very, actually quite interesting. That is, first, and the mantle structure will actually be, reorganized to form only one plume, and so that's like what I said earlier. And then this one plume structure actually will be organized such that it would actually occur, below this, this cap, right? The blue melt residue, right? Then so this is a kind of really sort of saying you have more, stronger plumes below a thickened crust, right? That would actually be below the southern hemisphere, right, on Mars. And then after that, then we start to see the differential rotation occur. That is, there is a relative motion between the melt residue and this upwarning, right? The yellow, upwarning, right? And then at time D, right? And somehow this plume material essentially stabilized and moved to the dichotomy boundary and then stabilized there. Okay. So this is essentially to say that it's let's actually, if we look at the, so here, what we see here is really the horizontal axis is the time. So, and the A, B, C, D, right, actually marked here, right, at 4 different times. That's 4 different slides we have here. And then the vertical axis here, this is actually the power of a convective structure, okay? And so what you see is that degree 1 became the most important power very quickly, okay, right? And then you see degree 2, degree 5, they're shorter wavelengths, but they're less important, okay? And so the degree 1 power, basically that means this is one plume structure. And then the red line really represent the angular separation between the center of this thickened, I guess this is light blue, high viscosity keel, and the center of the plume. Okay, so now you can sort of see at time B, right? And then this angle, this separation angle, is close to be 0. That's because that means the center of this keel and the center plume, the angle is very, very small. They kind of overlap, right? Then after that, we start to see the migration of the differential rotation happening, so such that the angle became larger and larger, eventually stabilized at 90 degrees. So which essentially is something like the time D here, right? So that really meaning that this original plume that may actually be below the keel, that may actually be responsible for the, crust dichotomy, then subsequently that plume migrate relative to the surface lithosphere, but got stabilized at the dichotomy boundary. Okay, right? So this is actually showing that without a keel, without the high viscosity keel, that's a dashed line, and the surface velocity is much smaller, orders of magnitude smaller than the interior viscosity. But once we introduce the keel, the solid line, showing that basically the lithosphere can actually move that motion of this sphere essentially is a differential rotation for us, right? And so we think this is really, this high viscosity keel may actually provide a unified model to explain both crust dichotomy and the surface rise. Okay, right. And this actually was published a while ago. Okay. So by now, I kind of covered the first two topics of the mantle dynamics, right? So what I actually want to do next is quickly talk about the moon. And the question here is, does the moon, mantle, presently have degree one structure? Okay. So remember I mentioned to you earlier about the deep moonquakes, right? And how the how the deep moonquakes, at least as we observe from Apollo missions, they actually all occurred, on the near side, right? So one question we ask ourselves is, are the deep moonquakes correlate with the marine basalts? Okay, or they actually just occur randomly, on the near side of the moon. It turns out that actually one study we did in 2012 really showed that all the deep moonquakes that we're seeing, they're mostly about 80% of them, they're highly correlate with the marine basalts. Okay, right, and so, but then this is kind of interesting. That is, we know the deep moonquakes that actually occur today, right? Present day, right? They kind of tell you about the present day mantle structure and the deformation. That's deep moonquakes, right? They record by the Apollo missions, right? Whereas the marine basalts, they actually occurred about 4 billion years ago, right? So those are the structures that really that occurred at very different times. If they're correlate, right, they actually, and then they probably mean something, right? So this is actually what we propose, in a study, right, that published in 2012, showing this cartoon, basically sort of saying, 3.8 billion years ago, and then there's this upwarning, okay, right, that, with this various materials, the yellow kind of upwarning, and that's hot produces the marine basalts on the near side. Then today, the structure may still be there, okay, the yellow structure. So the degree one structure, the present day near side, may still have this, residual features there that actually may contain a lot of water. Then we know the water would reduce the fracture strength to make the moonquakes easier to occur, right? So that's why we actually see this possibly this the deep moonquakes actually may be indeed it's asymmetric structure only occurred on the near side. Okay, so that's essentially what the kind of the two scenarios that we present back then. Okay, right. So then, and this hypothesis that we present basically, it's quite consistent with all the other studies. Okay, right. So now the one question is, of course, how we can actually test this idea, right? And that is, present day, the lunar mantle is got this asymmetry. The near side of the moon possibly is hotter or warmer than the far side, whereas all the kind of the deep moon occurred, right? So it turns out that we actually can possibly use the tidal response to detect this or to verify this. That is, if the moon actually got no structure, it's a one-dimensional structure, only varies with, say, viscosity or shear modulus, they only vary with the radius. In this case, if you apply the tidal forcing at a degree 20, degree 22, the tidal forcing, then the tidal response would also, be at a degree 20 and 22, the tidal response, okay? So the same harmonics as the forcing. But if the moon actually got a three-dimensional structure, and then the same forcing, the tidal forcing, actually will give you not only the 20 response, the 22 response, but also you will start to see at other harmonics, okay? And then Now, if you actually can observe or detect the other harmonics, then you actually can do this inversion to see what this lunar, mantle structure would look like. Okay, so in another study we published in 2012, we basically show that, if the moon got this degree 1 structure, that is a near side, far side difference, then we said the degree 3, you actually would expect very strong degree 3 tidal response. Okay, so that's really, so if you have forcing at a 2-0, right, then, then if you have a 5% variation in seismic shear wave speed, at degree 1 and also order 1, that is a near side, far side difference. And then you would expect response, in tidal gravity at the degree 3-1, okay? And that's this red curve here, okay? That's a degree 3, order 1, right? Now, if you actually apply the tidal forcing at a degree 2 and order 2, then you're going to get not only 3-1, you also got this 3-3, that's a green curve, okay, very strong, 3-3 response. So in this study that I published in 2012, and also my student published subsequently 2014, 2016, and we really proposed that the GRAIL satellite and data, GRAIL is a lunar mission, and to really measure the gravity in very high accuracy for the moon. And we kind of argue that maybe this GRAIL satellite data may help constrain, the degree 1 structure for the moon. But it's interesting. Last week, this just happened, last week in Nature magazine, and there's a study, there's a paper called really provide a confirmation of this idea, and really they use GRAIL data, and this is the title of their paper is called thermal asymmetry in the moon's mantle inferred from monthly tidal response. So what you see here is really, especially this green bar showing right here at different harmonics, how a degree 1 structure, order 1 structure, with 1% variation, you start to see the anomalies that that would produce, for 3-1, 3-3, right? So they actually come up with basically a model, saying that 4 billion years ago, and this near side that produced marine basalts, and this side is hot, partial melting. Then present day, and then this side is still remain hot with the near side below marine basalts, and it's actually also a lot of deep moonquakes occurring here. Okay, so in a way, this is really provide a confirmation to what we kind of proposed. Okay, right. So this just happened. This paper was published last week in Nature. So now for the remaining of my time, I actually want to quickly touch on the Earth. Okay, and so basically want to talk about a little bit about the Earth's convection. So Earth is different. Earth got a plate tectonics. It's what we call the mobile lead convection, right? So now, if I just want to quickly show you that if you for the Earth's convection, you need a weak, you need both a weak up mantle and also a relatively strong lithosphere to produce a degree 1 convection. Okay, so we use a temperature dependent viscosity. Now, this is a prefactor, the eta R in the temperature dependent viscosity. If the eta R is 1 throughout the mantle, then you got a relatively short wavelength convection, like what I showing here, right? Now, if you make the entire up mantle, including the surface layer, being weaker by factor of 30 for this right for this prefactor, and then you still got a very short wavelengths. Okay, right, a lot of the up warnings, down warnings. Okay, right. Now if you actually in this case, if you introduce a green color for the prefactor, that is for the top 100 kilometer or the lithosphere, you make that prefactor of viscosity to be slightly higher, then all of a sudden you produce this degree 1 convection, right? And that is one hemisphere is a blue or cold, The other hemisphere is warm and hot, the up warnings, right? This blue is the down warnings, okay? And so if you kind of ask what kind of viscosity that is you need, and this, this is horizontally average viscosity, then you have this weak up mantle, right? Then you have relatively high viscosity for the lithosphere. And it turns out that this combination is key to produce a very long wavelength structure for the Earth, okay? So now I want to show you a movie. So let's see how. Um, hmm. I wonder why it's a. Hmm. Actually, sorry, I want to show you the movie.
That's okay.
Um,
You can try, see if you get it.
oh yeah, nice. Yeah. So now this is a movie for the convection model. So you start with a relatively short wavelength, many
Actually,
down warnings, many
we
up
cannot
warnings.
see myself. I don't know about the others, but I cannot see your screen anymore.
Oh,
Yeah,
oh, okay. Let me see. Maybe I didn't share the. Sorry about that.
that's okay. That's okay.
Huh. Now can you see?
Yes,
Okay. Interesting. Why is so well, okay. I'll just in this mode for now. So what you see here is animation of this convection, right? You start with a relatively short wavelengths, but the convection will self-organize with this kind of viscosity that I just discussed, such that you would produce basically degree 1 convection, one hemisphere that is cold down warnings, the other hemisphere that is hot up warnings, right? And then um, and so then of course we think this is actually how you produce this degree 1 convection with this kind of viscosity structure, right? So now and so let's actually move back to this mode. Okay, continue to share. Yeah. Um, so can you see the screen now?
yes, yes,
Okay, good. Um, so, um, and as then of course, this degree 1 convection is really, we kind of show that it's quite a robust feature as independent of vigor, convection, heating mode, initial condition, etc. Okay, all you need is this kind of viscosity structure that we discussed here. Okay, so. Yeah, no, actually, I mean to get a laser pointer. Yeah, okay. So we actually show that, this feature, as I said, if we plot the viscosity, the ratio of viscosity of lithosphere versus the up mantle, and then this is like the vertical axis is the dominant convection wavelengths. It turns out that what we need here to produce degree 1 convection is you need the lithospherical viscosity in this neighborhood, around about 100, the viscosity ratios. Okay, then it turns out that Peter Bonga and others, they only look at this parameter range, whereas they only get a degree 5, degree 6 kind of viscosity, structure. That's actually because in their calculations, the lithosphere is just not very strong. Okay, right. So now the question here is, if since we showed the Earth's convection, would prefer degree 1, then but we know Earth got a degree 2 structure today, right? So the question is why does Earth have degree 2 structure today, not degree 1, right? So now this actually is where we think the supercontinent actually became very important. So then, well, what actually happened with the supercontinent, right? And the answer is actually quite simple. That is, the mantle below supercontinent will actually get hot, okay, right? But as to why it's getting hot, it's actually there are two different views. One is actually thermal insulation. Supercontinent may actually insulate the mantle, so the mantle get hotter with time. And another explanation actually is this is kind of a hot upwarding return flow in response to supercontinent subduction. So I actually will show you how this actually, the second scenario may actually be the case, okay? And so now this is another movie that I hopefully see if I can get this to work. So now, so we know when you have, single down warning, then another hemisphere single up warning, right? Then this kind of degree 1 convection will push all the continental blocks into one hemisphere, okay, right? So then you actually form a supercontinent above the down warnings, okay, right? And so the question here is, if you, after you form supercontinent in, in this hemisphere with down warnings, then what will actually happen after, right? So it turns out that, so then I have to, so I think actually, I have to, I may have to kind of stop sharing a little bit and going back to another mode. Let's see, yeah. So give me, now I can come back to share, share the screen again. So now, so here I'm going to show this movie, sort of saying that is once you actually form supercontinent, then the continent cannot be subducted, right? So the subduction can only start happen at the boundary of the supercontinent. The supercontinent here is actually represented by the green kind of cap, right? Now you see the subduction will actually occur around the supercontinent, right? And then so that subduction actually will cause return flow below supercontinent. So then you start to form, and it's a secondary, plumes below the supercontinent. Okay, so this is actually, so this is two super plume now. You start to have two plume system. Then these two plumes are actually antipodal. Okay, so that's actually how you can get a degree 2 structure. Okay. So yeah, it looks like I had some problem in showing the movies, but anyway, so I think now no more movies, and I think we should be okay for the rest. I only have a few slides left. Okay, so yeah, sorry about this. Now. So this is actually what we kind of propose, what we call the degree, this is a 1-to-1 model. And that is, when you have a degree 1 convection with one major up warning system, right, and one down warning system, that's actually how you form supercontinent in this down warning hemisphere. That is the down warning hemisphere. Essentially, all the down warning will suck all the continents together to form supercontinent at the surface, right? Then this then the supercontinent subduction then will induce secondary plumes. So you're going to have two antipodal major upwarning system, right? And one actually is immediately under supercontinent. Then that secondary supercontinent, super plume actually will tend to break the supercontinent. Okay, so then once that happens, then you can possibly go back to this degree 1 convection again. Okay, right, and so this is what we kind of call the mantle convection. You tend to have this degree 1 to degree 2 to degree 1 again cycle, and at surface you would actually have the supercontinent cycle. The supercontinent will form and break and form again, etc. Okay, so this is sort of like a framework that we proposed, right? And so this actually have interesting implications in terms of volcanism, the large Euclid province events, right? And now you can imagine during supercontinent formation, and that's all the continental blocks, they tend to move to this hemisphere with cooled down warnings, right? So in this case, you would actually reduce the volcanism, the level of volcanism, right? And so that's essentially what we actually see in geological record during supercontinental formation, and you see the minimum level of magnetism. Then, of course, this also can help us to explain why the African and Pacific superplumes are antipodal, like what we see here, right? Antipodal, the degree 2 structures. So what we see today, essentially, is the aftermath of breakup of Pangea. Okay, so we're still in this degree 2 mode, right? So that's essentially what we see today, right? Degree 2 structures. And so this would also imply that African anomaly, the superplume African anomaly, are younger than Pangea, because really it's a Pangea supercontinent form first, right? You see, then you form this, this is African superplume below Pangea, right? And so, but the Pacific anomaly would be much older. It turns out this has also been supported, by various study, subsequently, the study that I list here. Okay, so I think that's all I have to say today. So it's, turns out the animation didn't work as well, but anyway, and so here I kind of list all the major conclusions. I'll just very quickly kind of discuss quickly a little bit about it. So basically, I kind of argue that the mantle dynamics is responsible for producing non-wavelength structures, degree 2, degree 1 features for the Earth, Moon, and Mars, and also the lithospherical and the mantle viscosity structure, radially stratified, is really the key to do this, okay? And for planet with a stagnated convection, that is Mars and other planets, you can still have lithospherical motion, but the only possible mode of lithospherical motion is a lithospherical rotation relative to the mantle. And that can happen, with the right conditions, such as, the lithospherical thickness variations, okay, right, as I showed. It turns out that we suggest that may actually provide a unified model for Martian crust dichotomy and surface rise. And then, it turns out that the moon actually, even present day, got a degree 1 structure. And this is near side, far side. And really, so that really means throughout the moon lunar history, okay, from, 4 billion years ago to present day. And then we also discussed about the Earth's supercontinent, how the supercontinent cycle and the mantle degree and the long wavelength mantle convection work together. And so this is what we call the degree 1 to degree 2, degree 1 again, this kind of structure evolution models. Okay, so well, thank you for your time. I think actually looks like it's longer than what I thought I would be able to finish. Okay. Yeah, thank you.
Thank you very much, CG. It's always a fascinating topic to hear about convection in planetary, in planets, and also how it is linked to the viscosity profile. It's a very interesting topic. So thank you very much. I'm going to open the floor for question or comments. So you can either unmute yourself and ask a question, or put a comment in the chat. Whatever you prefer. No question?
You all believed.
Yeah. Okay, well, so maybe while everyone is thinking about the question.
Yeah, I see that.
Yeah, Cindy.
Cynthia, yeah. Yes?
Yes, Cindy.
Hey, Shijie, thank you so much for a really excellent presentation, and where you also, in a way, presented to students who are attending a way to take a very difficult problem and break it into the most important, or evaluate the most important components of a system. Particularly related to the moon, you're looking at the convection and or you've evaluated the internal processes, but external processes have also played a role in the evolution of the crust of the planet. Could you maybe give an idea of the next steps then, that once you have a first order model for the evolution of the moon, or for the internal structure, how one might have you looked at the role of large impacts on changes to the structure, depending and early on in lunar history?
Right. No, that's a very good question. I mean, so I guess I came from the Earth, uh, kind of earth science background, right? So and then if you look, to me, the endogenic process, it's always been like the first order, right? To me, whereas you know, when I start working, this is really through Marie Zuber and Mark Parmentier into the planetary community. Of course, the impact process being considered as being very important. So of course, for good reasons, right, it kind of occurred in the early history of in our solar system. So for example, there is this, if you look at the moon, there's this source for Aitken Basin, right, and so it's really, that basin still, we can still see it. It's a major impact basin. Happened very early on, in lunar history, right? And so clearly, for the lunar history, early history, the impacts, sort of dumped a lot of energy into the system. There's quite some studies, including some studies by my former students, and they look at how this may actually really work together. The impact process may actually really influence. I guess what I've been doing really is really focus on one aspect of the process. Okay, right. I guess in reality, both exogenic and endogenic process probably played a role. And then of course the impact only happened in the early on. Maybe the first 500 million years for our solar system, right? And then subsequently will all have to be controlled by the endogenic processes. So, I guess, I cannot really give you a very good answer, and that is how these two processes actually come together to play, right? And there are some studies that look into this, and then the model just became very complicated. Because the impact process, there are certain, there are certain arbitrariness with it, right? Whereas the endogenic process is mostly just fluid mechanics. So you can, we can view that almost as the first principle calculations. Yeah, I guess that's probably all I can say. Yeah, but it is important process, especially for the first few hundred million years, for Mars as well. The Mars, and there are also suggestions, on how impacts played important role in forming crust dichotomy, and also the sources, due to impacts. Actually, well, the more recent study from seismology, I guess the Martian seismology, the InSight, and even even this year, there's a paper from the ANU group, and they actually show that perhaps the endogenic process may actually explain the seismic results from InSight better. So the jury is still out there. I guess what I present is really one possible mechanism. Okay, and so this is why it's interesting, right? Science is always and there will be a way to check on ours, right? And through observations. And I think the Nature paper published this week was really, I feel like, quite excited, right? Because the tidal deformation can indeed help to provide constraints on the lunar mantle structure that, for today. The showing is a degree 1 structure. Okay, yeah.
Thank
Okay.
you.
Thank you. Yeah.
Thank you. So we have Richard with a question.
Okay, yeah, go ahead.
Richard, you can ask your question.
I think Richard,
can you hear me now?
Yes.
Yeah, oh, lovely. I really like the whole talk, the way it all brought everything together. I liked the split between the degree 1 and degree 2, depending on the supercontinent and the intermediate stage. What about the core mantle boundary? Because wondered, I'm not an expert in any of this, but I've wandered back from views of the stability of the core mantle boundary or the instability, and Bernhard Steinberger's work in principle convinced me that at least consistent to say that it's a stable degree 2. So in your models, does that change degree 1, degree 2 as well? Or is that...
Well, I kind of I skipped that part because it is a fascinating topic, right? And so you're talking probably the LLSVPs, right? The large,
Yeah. Yes, and
the volcanisms related to that, and
whether the plumes. Sorry.
Yeah, we actually, that was that itself is a big topic, and so we, so. For those who are, not following this topic closely, basically, there is this one view that is a degree 2 structure, is for the Earth that we see today, has been forever, right? There's a Kevin Burke's view is really since Archean. The degree 2, rise, structure that we see today is really since Archean, and also the Torsvik and Bernheim Steinberg, and they've been so they're sort of saying at least since Paleozoic, like 500 in the last 500 million years, and so there is some evidence for that, but I would argue there's the evidence beyond 200 million years is very weak. And the reason being very simple, because there's very little volcanism, as I mentioned, older than 200 million years.
Not much data. You can do all sorts of
that's exactly what. Exactly, because of course, and so, but I kind of I referenced a couple of papers, more recent paper, like for example by Nicholas Fleming. There's a 2022 Nature paper. And there's also this year, there's a paper by Ellen McNamara and others. And there's this also paper by Ducey. And it feels like the more recent studies overwhelmingly support this idea that the core mantle boundary structure is more mobile, it's dynamic.
Okay.
In response to subduction. And so therefore, they're not really, this degree 2 structures are not there forever. I guess that's a kind of way to say.
Okay, thank you.
Yeah. Okay. Thank you. Yeah.
So we have a comment from or question from one of our students, Sylvain. Why do you think Earth evolved into a degree 2 structure while Mars and the Moon show degree 1? Is it a matter of size, cooling history, or tectonic regime?
Yeah, and that's a very good question, right? And so, as I mentioned, it's really, I think the supercontinent cycle played a very important role. So by supercontinent cycle, of course, that really means that, you would have this, it's really, the plate tectonics, right? So we know the Earth got a plate tectonics. Earth is the only, I think Earth is the only planet that we know actually got a plate tectonics, and so that means the surface is kind of surface of plates, they actually move around, right? And so that's how we have supercontinent cycles. And so the supercontinent, once supercontinent form, as I showed in the movie, right? So once you form supercontinent, the continents, they're buoyant, they cannot be subducted. So then the subduction can only occur at the boundary of a supercontinent. And so that's how you actually can turn a degree 1 structure into degree 2 structure with the two, super plumes, right? You after supercontinent got formed, then you actually create a second super plume immediately below supercontinent. So that second super plume, will give us the degree 2 structure. And so that's, to me, that's really what happened. So yeah. Yeah.
Okay, thank you. Any other question or comments? Maybe I can ask a couple of questions. In one of the model where you create these two order structure.
Mhm.
When you start the model, there is a transient before you get that. How long is this transient before you get to the stable order 2 structure?
Yeah, okay, that's a good question. That's really, I think that's a really, really important sort of important feature when we try to distinguish between the thermal insulation, right? You know, remember I mentioned it at the beginning. So we know the supercontinent, can actually make the mantle below hotter, right, with time. One idea is due to through the thermal insulation idea. This is Don Anderson and many others, subsequently after it, right? Then the other idea is actually what we, I would say maybe, in Mike Gurney's early study, there is evidence for that already, but he didn't really explicitly kind of mention that. And so then I think in our 2007 paper, we really show that it's really due to, this is the second mechanism, the return flow, right? So you have a subduction at the boundary of a supercontinent, then the subduction will give you kind of return flow of hot upwarnings below supercontinent, right? So, in our calculation, that process can happen, in matter of 1/term, right? So that's like 50 million years ish. You can get this upwarning already going. So the return flow, the second upwarning, right below supercontinent, you can form that in really matter of 50 million years. Whereas the thermal insulation, you can ask yourself, the thermal insulation essentially is you kill all the heat flow from the surface, out of the supercontinent, right? Even if you just zero heat flow out there, and it will take hundreds of millions of years, to raise the temperature below, right? Because the radiogenic heating is relatively small, right? So so this is what so the time scale, I guess, to answer your question, really at least from our model, the secondary sub supercontinent plume, super plume can form very quickly, because it's return flow. So it's really 50 million years, yeah.
Okay, thank you, Shijie.
Yeah,
And
okay.
I had another question, but it's not related to the model. It's related to actually the 2 super plumes. We kind of see in your first slide actually that they would be, okay, it's a super plume, but within that super plume, there are also some other structure, like especially under the Pacific. I think it's even more distinct from the tomography, that we have a substructure within that a super plume. So is it because we haven't got the picture refined enough, or
Yeah, I mean,
yeah,
like
in this, like if we go under the Pacific,
right.
I mean, could we identify a number of plumes, individual plumes or plume source within that region?
Well, so, and those are the subduction, right? So
Yeah, but for the low velocity anomaly
yeah.
in the
Oh,
Pacific,
yeah.
yeah,
Yeah.
you see this, they are almost like some dots or points,
Right.
or
Yeah.
which are even more anomalous. Let's put it this way.
Yeah.
Is it because we have a blurry picture, or is it we
I
assume that they would be like individual plumes?
Yeah, that's a very good question. I mean, again, I know Barbara Romanowicz and and Davar, and they actually had a paper not long ago, like a few years ago, where they really discussed I guess the plumes in this upwelling system, right? The multiple plumes, and so. Yeah, I mean, it's I think some of the features are real. Although tomography models, I don't know to what extent the different tomography models will agree with each other on that, on the details. But I can certainly imagine that, you can have multiple plumes in this, say, Pacific system, right? Super plume. You can have multiple plumes, not a single, really one plume. So they actually really, this one upwelling system would actually consist of multiple plumes. I think there's a good geodynamics argument or convection argument for that, as Anne Davos showed. And there's also good seismological evidence for that as well. I think that's a really interesting topic, for future studies.
Yeah, especially because it doesn't look so obvious for the African super plume. Like one is in the ocean, so there is no, it's not the same lithosphere. I don't know. It's like the two features are distinct, while okay, they're super plumes, but they seem to be distinct for some reason.
Yeah, I mean, there's two, even there's two systems. They have a different chemistry. That Pacific and the African super plumes, they have different chemistry. Some of the more recent studies they really showed that. And so, yeah, it is still, I think it's still a very fascinating topic. Yeah.
Yeah. Okay, so are there any final questions, or should we close here?
Okay.
I think, yeah. So I think we will close here for today. But again, thank you very much, Shijie. It was an excellent talk, and also very good for our students at ICTP-EAIFR. So thank you very much.
Oh, thank you, thank all of you for listening. Yeah. Okay.
So I'll stop.